This is a demonstration of Agile design using advanced hardware data types in the Rapid Open Hardware Development, or ROHD framework. In particular, we're going to use test-driven design to add a few features to a floating point hardware component in the ROHD hardware component library. So let's first look at an advanced data type in ROHD for floating point arithmetic. This is our class for representing the signaling for a floating point. And you can see it's a composition of other signals. Here we see that there's an exponent, mantissa, and sine that represent the structure of a floating point signal in ROHD. Now, when we look at advanced data types, we need to consider two facets. One facet is it's a complementary class, which is for the value side of the computation we're performing, and that's the floating point values. And then we consider this class, which is the signaling side, which represents the logic structure of a floating point computation. And one way to think about this is the value side is really the software model, and it is actually going to represent the computation in software. And the second is the actual hardware construction side, which is going to be used to connect these logical signals and bits to hardware. And we use the software model to help us validate the hardware as we test it. Now, if we look at the simplest possible kind of signal, that's logic, and that's basically either a single bit or a bit vector. And the two facets of this signal are the logic value, which is representing the Boolean logic, and of course then the logic itself, which is the signal that can be connected to different kinds of hardware. And what you can see with logic value and why it's a software model is if we look for things in here like the slice operation, right? This is going to actually allow us to look at subsets of the bit widths of the logic value and to actually operate on that. But also you see that we have conversions to native types like integer, big int, bool. We have operators like bitwise operators and or. And these are all working in the native math of the operating system we have. And so these can be used during validation. So we can compare, we can operate on the logic values and make sure that they, on the software side, we compute something we want to compute, and then on the hardware side, we can validate that we actually got that result. And so if you look through this, we have a lot of the math operators, the logic operators, comparison operators, and so on. And so what we can do is build a full software model of the computation on the test side that we're trying to do. Here's equality, for example. I'll scroll to the end and show you all. Here's shifting operators, so we can actually do bitwise, bit shifting, and then make sure that our hardware is actually computing the same result. There's even down below, I think there's sign extension. Yeah, here we have different kinds of sign extension, so we can actually do mathematical operations and make sure we get the proper signs. And so all this is on the software side. So that's what logic value gives us, is a class that lets us do a software model of the computation. Now on the logic side, the actual signal itself, one of the things that's critical is we see logic value get, right? This is the way we retrieve the current value of the signal as it's operating in hardware, and we can use that software model, that logic value model, as a way to check those signal, the value of the signal, that it's doing the correct thing. Again, in logic, we have a lot of operations now that deal with connections, right? So this logic class is used for connecting hardware and for generating hardware. And any of the methods that this class has have mostly to do with constructing hardware. Here we can see also an important method is the put method, which allows us to actually store values onto the signal. And this is important because we can use this in subclasses of logic to make sure that the right types of values are stored. And I'll show that with the floating point class. Here again, we have operators in logic. However, these are different than what was in the logic value side. These are actually hardware operators. So these are constructing hardware that do these operations. So for example, the comparison operator, the bitwise AND, these are going to construct gates on the actual logic bit vector to perform these operations. And so you can use these operators to construct more and more hardware. So scrolling to the end, let's see if there's anything interesting we can show. Select from is an actual bus selection. It's an index into a bus, and this is again hardware that's generated to access the bit vector. So analogously with our floating point class, we have a value side and the logic side, the signaling side. And on the value side, you can actually see that we have custom methods for dealing with floating point values. For example, if we look at is operators, right? We can check that, is this floating point a subnormal, which is, it has an exponent that's 0, and the leading one in the mantissa tells you the most significant or the J bit. Is it infinity? Is it 0? These are all software model constructs. You can see is the exponent all ones is actually doing a native math comparison in the system. Conversion to double so that we can actually validate against the native double type is normal. These are all methods that we used for creating a software model of floating point math. Here we have operators like multiplication, addition, and these are all going to be using the native math of the system, the operating system we're in, so that if we build hardware, we have something, a model to compare against. And on the logic side, we can also see, similar to what we saw on the native road logic, we can also see that there's hardware that we use, hardware that we can construct from the floating point class for basic operations. For example, one of them would be, say, is normal. And here, in this case, we're actually constructing hardware to check if the floating point signal is actually a normal signal. So we're going to make sure that the exponent is non-zero and so on. And so this is all hardware that can be constructed using the floating point signal data type to actually help us with constructing hardware. Now, I mentioned put in the logic case. Here's a case where the put is actually doing something more intelligent. It's making sure that you only store onto this signal, this floating point arithmetic signal, that you only store the right widths of floating point. For example, you might have two different kinds of FP 8-bit floating point values or signals, and you only want to store the correct one with the correct exponent and mantissa onto that signal when you're doing software testing. So this is a way to enforce or do more strict typing when you're doing testing of this data type and when you use it for hardware construction. And finally, we have another class that we use for in the floating point case, which is, we call it the populator. And the populator is just a helper class. Think of it as part of the floating point value. It's just something that we use to help us do more complex population of those bit fields or those inside the floating point value. And so, for example, we have conversion from binary strings, right? So that interpreting the binary strings, also converting from big ints, and importantly from constants. So there are floating point constants that are named, but for different floating point widths, they have different bit fields. So for example, the smallest positive subnormal is constructed this way here, and we can store that now using this populator into a floating point value to initialize it. And so the populator is something we use to make sure that we can actually populate floating point values correctly on the software model side. Here's an example of converting from double, the native double, and storing that in the floating point value correctly. And that will help us with validating floating point hardware because we know our values side has this class that has strict typing and has all these methods for dealing with floating point values. So taken together, these three classes, the floating point class, which is the logic side, the signaling side, and the floating point value, which is the software model side, as well as its populator. This is a part of the value side. These three classes form what would be an advanced data type in the ROHD hardware component library for floating point. And let's look at how we would use these classes together to test floating point hardware. So here's a test on the right, and it's this is an adder, a floating point adder that is a dual path adder, so a fairly fancy adder, and it takes two floating points, the signal type, and adds them. Now remember they're variable width, and so it's doing the bright computation for that width. And we're going to use the software model to make sure that this floating point hardware is working correctly. So, but one thing that's nice about variable width floating point is that we can exhaustively test it at narrow widths and cover the corner cases of floating point. Now, I mentioned the populator is used. We actually use a helper class here for the populator, so I want to talk a little bit about that. So here's the construction of a populator, and what we're doing is what's called currying. We're actually creating a function that already has the width specified. So we can just call this function, and we have an initialized floating point value that we can then populate. So here is our validation loop. We're either doing additions or subtractions. We're going through all possible values of the exponent field and all possible values of the mantissa field for the first floating point value. And then we're initializing that with those integers using the populator. We're doing the same thing for the second floating point value, but we're allowing it to be a subtraction conditionally on this loop. And importantly, I showed that we can store these values onto the corresponding floating points, and those widths are checked so that the floating point is matching. I didn't show you where I constructed these floating points, but this is a group test, and in the group test at the very top, we're making an assumption about fixing the exponent mantissa and constructing to initial floating points according to those widths. So back to our test case, we've stored those values, making sure that they match the types, and we compute the floating point value off of the final sum that the adder has produced. So we extract the floating point value off of that data type. In the native system, we compute the add ourselves, and then we also compute what the expected value is. Basically, we in terms of the floating point value. So in one case, we don't want it to round, so we use a populator that takes the double and converts it back to a floating point value and doesn't round it. And in the other case, we use the native method, and this will just round. And then we compare. And so this test does an exhaustive test for exponent 3 and mantissa 4 widths. And so it'll run through and make sure that everything matches what we expect, including nans and infinities and sines are all validated using this exhaustive test. And this usually runs in about 20 seconds. So we saw in this test that we ran that we could actually use the advanced data type, floating point, and floating point value to actually do validation of this dual path adder. And the typing actually kept us from operating at the bit level. We were actually operating at the level of floating point value and double and doing comparisons at the software level with abstractions. It's also interesting to see quickly what happens when you debug this. So if we set a breakpoint in an interesting spot where we can get some interesting values, let's try debugging this. And we'll see when we debug, we can see the values changing. So let me get through a couple of an interesting point where we have some positive numbers, some positive exponents. All right, so now we see a positive exponent. Let's go down to this expect and continue so we can see both numbers. All right, so we see, let's continue a little bit more to see a positive FE2. There we go. So now we're seeing FE1 and FE2 actually have non-zero values, and now we're actually seeing a sum happening, right? With the expected value computed from the software model and the computed value coming from the actual adder. And so of course, what's nice at this point is that you can go inside the debugger and actually see these values, or you can have them displayed
in this debugger because they are native Dart types, this floating point value. You can actually understand using the toString field method what the different fields are, and you can see them change as you simulate. So nice ability to integrate the software model with native debugger in Dart. So let's go into the problem of understanding what our value type is like to work with. And we should probably create a small group of tests that we can use to explore the floating point value before we begin actually our modification. So let me, excuse the cut and paste, but I want to show you a simple way to create a group of tests for some new feature. So this is sort of exploring the way we do test-driven design because we're going to actually modify this data type and the arithmetic units. So borrowing from what we saw before, this is a basic software model. We're going to use 4 and 4 for the exponent mantissa. We're using a currying FP populator, FPV populator, so we can populate these values quickly using those widths. And then let's print out some basic floating point values. So let's see what these look like, and then we'll step through. Okay, so the very first one is 1, and a 1 is a 0 with all ones leading is halfway through, and that's considered the bias point of a floating point number. This is for a narrow 4 wide, and for a regular single precision, this would look very similar. It would just be 8 bits wide. We can see we printed out the floating point value, how it was represented in bit form inside the system. This is on the value, the floating point value object, and then how it converts to double. So it's 1. We can create a small normal, which is the smallest exponent we can possibly have, which is a negative exponent, because it's 7 minus 1 or negative 6. And this is what it turns out to be in double form. And we check, is it normal? And it says yes. A subnormal, this is a fairly big subnormal. It's not the biggest subnormal. The biggest subnormal would have all ones. But again, we can see that it's half the size of the smallest normal, this particular one, because it's shifted over by 1. Normally the implicit 1 sits 1 to the left, and so now there's no implicit 1. It's the leading bit in the mantissa. And so we see that that subnormal, this is the value that it converts to. And we're going to use this copy in a later test. So we're just showing that we can copy that to another floating point value and use those bits again in this floating point value and see that it produces the same result. So we'll be doing some modifications for that. So the actual change we want to make, the feature that we want to add, is actually 2 features. One of the things that we like to do in floating point is treat the subnormals that I just showed you as 0. And in, say, a floating point component, there are 2 possible ways of doing that. One is if you see these subnormals come in as inputs, you immediately convert them to 0 and treat them as 0 throughout. And that's called denormal as 0 or DAZ. And then the other feature is if you happen to compute a subnormal, say you subtract two very small normal numbers and you get a subnormal, then you want to output it as a 0. And that's called flush to 0. So DAZ and FTZ are the 2 features we like to add to our components. And we can think about how we would do that if we were to look at our floating point adder. So let's go look at the floating point adder. So one way we could do this is we could say, this is our dual path adder, and we could add a Boolean configuration that said DAZ and FTZ, 2 Booleans, and we could configure this adder to do that. And then we would do that for every component, and that's sort of one way to think about it. But it's very much a sort of a bit level hardware-like thinking about the problem. And it leaves us a validation challenge, right? That now we have to actually replicate that same thing in every test that we do. We have to actually think about, oh, we set that, so now we got to make sure we zero out our software side to make sure that we compare correctly with the software model. And so that's one way to think about it. But the other way to think about it is to say, well, wait, we can pass these types in. Notice that our floating point adder takes in a certain floating point type. So what if we change the type? And we said, well, the type behaves a certain way. It behaves as such that when you ask it, hey, there's this bit vector that represents the floating point value, and if it doesn't have any ones in the exponent, then treat the whole thing as zero, right? Just treat it as zero, 0 0.0, the number. And if we do that, then we can use a type to actually pass in, and we have both inputs and outputs. So we can also use the output type to say, well, if we pass in this special class, this special type, then it'll also do the same thing on the output. And so then we get DAZ and FTZ as features for any component that we implement, because we're going to condition it using this type. And it's a much more structured way of doing it. Plus, it buys us a software model of this. So how do we go about doing that? Well, we could derive from floating point and from floating point value. We could derive, this new type, which is, something like floating point value, subnormals as 0. But it's likely a lot easier just to add a flag when you reconstruct the type that says, hey, this is an optional feature, which is treat this floating point number as 0 whenever it goes subnormal. And so that's the approach that we're going to take, is we're going to actually change the floating point advanced data type, which is its value and its floating point, to actually have this new feature, which is treat subnormals as 0. And then it becomes really just one feature in the software model. And then in the hardware side, there'll be a couple places where we need to actually look for that flag. So we'll go and do that now. Okay, so we decided that we're going to actually introduce the normal as 0 and flush to 0 as a new Boolean in the floating point value data type and the floating point data type. So let's start with the testing side and just think about what we want this to look like. So what we really want is to say, we have a flag that says, let's treat subnormals as 0. And by default, that would not be true. We would always use subnormals as our floating point type. And let's pass into our populator the same flag, right? So now this is the software model we really want. And then we can use that in our tests when we populate. For example, we can say, here's a subnormal that we want to treat that way. So we're going to say subnormal as 0, and we're going to set that to true. And so we're going to expect that this is actually going to come out as 0. But when we copy it, since we used an FPV populator that didn't have that flag set, then we're going to expect this one to turn out to be the normal value that it had. So that way we have a way to, interpret the bits that are computed as either, the new software model, which is subnormal 0, or, we can check that, oh, those bits are set high. It actually is a subnormal. We can read the actual double value. And that'll help us with validation to be able to do it both ways by copying the original. So what's left to do here is we actually need to create this feature in our floating point value. And we'll also have to build the feature into the floating point itself so that the floating point hardware can see, this type. So to see this new floating point as distinct. So let's go to floating point value and start implementing this idea. Now, we had this something like this, another feature we called explicit JBit. So we're just going to use the same methodology that we did to pass this feature called explicit JBit. And so what we really need to do is just replicate the same thing that we did with JBit, and we'll start that process here. We'll say um, treat subnormals as 0, right? And we're going to say late final. We're going to create um, an actual storage of that, which is going to be bool, and we're going to call it subnormals as 0. And then we're going to actually create a getter for it. So bool get subnormal as 0s. There we go. So that's one change that's significant that we need to make. And then we're going to do the documentation on it. Okay. So what's next? Let's go and look at explicit JBit and just follow the pattern. So that way we can just replicate it here, and it will look at the two kinds of changes we need to make. So one kind of change is to actually pass in this Boolean into the construction routine. So we can have a bool subnormal. And then of course we also have to pass in the fields. So subnormal. Okay. And what we need to be able to do now is do this for all of the routines, and you can see there's 19 changes that need to be made to actually pass this through all of the places that it's going to be used. And we're just going to parallel the explicit JBit. So I will go do that now. So now we've made the changes for subnormal as normal and passed them or threaded them through the different constructors we have. So we can see here we have each place where we had that flag, the explicit JBit flag. We've passed also the subnormal as 0 flag. And you can see that on the right, our test is actually doesn't have any errors in it right now. The syntax errors are gone because we now have the appropriate flags. We still have some things to change on floating point value. If you remember, we were talking about floating point value being interpreted as 0 whenever it is subnormal. And so there's a couple of routines in here that it makes sense to go modify beyond just constructing the flags. One of them is this a 0? And so that's a routine that we need to modify. So let's see. Here we have it's a 0 if it's either a positive 0 or a negative 0. And obviously there's one other case, which is we have the subnormal as 0 and it is subnormal. So that's a case that we need to worry about. And then finally to double. And so when we're converting to double, then if we have a 0 exponent, then here we are here. Clearly we need to make sure that we don't convert the mantissa. We actually make it 0 if it's subnormal as 0. So let's modify that. If subnormal as is 0 and it's subnormal, then we can just make the double val 0. There we go. All right, and now there. Okay, so now we've changed what we believe we need for the floating point value. One thing to remember is that we also have the populator. And so if we look for that, we need to think about where the populator might actually need to worry about 0. So let's go look at the populator. And here we are in the floating point populator. So the populator needs to think about what happens when we have sub-0 as subnormal as 0. So we have a similar flag to set, but we use the floating point value that it's filling, the unpopulated floating point value. So we'll do the same thing. True if subnormal numbers are treated as 0. And we'll do a getter for that. There we go. Typo. Okay. So let's think about what else we might need in the subnormal. That is to say, the subnormal case for the floating point populator. So we know that we also have double conversions in the populator. So let's go look for those of double. And we see here enough double, we're going to have to do something about the fact that when we have a double that's small enough, that's going to create a subnormal, that we need to actually convert it to an actual 0. And so the natural place to do that would be near the very end. And we would say something like if subnormal and let's see, the x value is less than or equal to 0, then we're going to convert it to 0. The rest of this AI is wrong. Okay. And we don't need to worry about setting that to 0. So let's see. The other one is double unrounded. So let's go look at that one again towards the end. It's the easiest place to override the logic here. So this one's a little bit trickier. It seems like we should change this clause to say subnormal as 0. And then we want to use a 0. Think about this if this is true. Okay, this is not quite true. What we want to say if the resulting exponent is going to be 0, so that would be e plus bias is less than or equal to 0. Then we would know that we are subnormal, as 0 would be, we would want to convert that to 0. And so now we've completed the populator, we believe, and there's no other, oh, we have random. We have random as well. So we need to do something about random, and random is going to be very similar to the doubles. And so let's think about random for converting subnormal. So yes, with random, we're going to have to watch the mantissa as well. So let's move the mantissa to the bottom and do a very similar check on sub-0. And our exponent is actually 0 that we generated. Then we're going to want to create a logic value 0 with the right width. There we go. So now if we're generating a mantissa and it turns out that the subnormal as 0 is true and the exponent is 0, then we'll actually return 0 for the mantissa. And so this will be correct for that case as well. So at this point, we've completed the floating point value support for subnormal as 0, and we'll just check our basic smoke test here for if that is working correctly. So let's examine that. All right, so we're seeing that this third case, subnormal, is actually returning 0. So it's doing the correct thing, and it's not normal. And we're also verifying that when we copy it into a new floating point value with a populator that doesn't set the bit, doesn't say subnormal is normal, it's the normal populator, that we actually get the same value as we would have gotten initially. So that flag is not active when we copy. Okay, and now on to actually validating that more extensively. We need to write a more extensive test. So let's work on that. We will copy paste an example test. So let's try that. All right. So we're going to run this test. We need, unfortunately, we need to write the exponent limit. Oops. There, and the mantis limit there. And now we have our loop. If we look at this loop for testing subnormal, what we're going to do here is we're going to convert from integers to floating point value. We're going to do it two ways. We're going to do it the normal way, and we're going to do it with a subnormal as 0. And we're going to expect them to have the same string. The internals are the same, so they'll have the same string. But when we have a subnormal, then we're going to expect the subnormal as 0 version to be 0. We're also going to expect it to declare itself as 0. Now let's run this test case and see what happens. All right, we got this test case to run. Yes, and you can see this makes sense that this is a normal case, and so in the normal case they will have the same double value, but in the subnormal case the one with the flag will always flush to 0. And so now we have a complete software model for floating point value with this flag that lets us say, treat any subnormal that you might get as 0. And we'll be able to use this both for the input type and the output type for denormals as 0 and for flush to 0 in the actual floating point components. So we've completed the floating point value side of subnormal as 0, that feature. And now we need to add it to the signaling side, or the logic side, which is really mostly a type system that the floating point components will key off of to implement this feature. So let's go look at the floating point logic. And again, we will look for the explicit JBit feature as a way to parallel. And we see it's being threaded through the different constructors. Here we see we need this getter scheme for actually storing our Boolean flag for the data type. So bool get subnormal as 0. There we go. And then we'll add this flag. Good. And now we'll add the documentation. There we go. And that's good enough. And so now I will go thread through the flag here like this. We'll just be changing these flags to throughout the constructors. So I'll go do that. And so almost all of that, those edits were just changes to the threading of the flag through various constructors. The one place where we need to be very careful is to make sure that this put actually does the check. So we need to do the check for subvalue to 0, subnormal as 0 is true, matches the value that we're storing, and so that's all we need to worry about. So and so then we're done for the logic side. So now floating point logic supports this flag, and we can move on to actually building modifying our floating point adder to actually respect these flags. Okay, so let's go consider modifying the adder, but first let's use the agile method of writing the test first and getting it to fail. So we'll look at our adder tests, and we will create a new group for the DAZ and FTZ tests. And I will cut and paste a basic test first. So let's do that. Here's our group. All right. So let's walk through what this group's going to do. So we're going to prepare for an exhaustive test. So we just grabbed what we need. We're going to use very narrow widths for now. We need a floating point constructor for the signal type that actually passes the flag, subnormal 0, as well as the populator. So in the actual test itself, we're going to align the subnormal as 0 flag for both the constructor of the floating point as well as its value. Of course, the put is going to enforce that. And we're going to construct a couple of input, or an input that has both as subnormals, so we can force the failure as we drive this test and drive the functionality. So we're going to do a small loop, which is enabling subtraction and trying out different normal as 0 flags for the two different inputs, so that hopefully one or the other or both will be treated as 0, and the adder will produce the right result. Now, something to be very careful about is that we don't want to have the adder produce a subnormal and then read it off and convert it to 0 on the outside, and think that the adder did the right thing. So what we're going to do is we're going to copy it out without making any modification to the value. So we'll just copy it out into a normal floating point value type without a flag, and that way we get the actual bits and the actual double that it represents without any kind of value conversion. So that'll keep us safe there, so that our software model will be actually validating what happened in hardware. And then in this case, since we're doing denormal as 0, this isn't going to be an issue, but when we're doing FTZ, it's going to be an issue. And again, we're going to just use our usual test case for the dual path adder, which is to check the unrounded and rounded cases of the double that our software model produces. And so if we run this, we should have no problems because we're not doing anything special. We're just using denormals as normal. We're using subnormal as 0 as false. But when we turn these to true, we expect that there will be some failures because our floating point adder is not doing anything right now about subnormals. No special treatment, no DAZ is being run. So, and there's our failure, right? So one of these was expected to come in as 0, and in fact it was this second one, and so that makes sense as an inner loop, and so of course the expected value is smaller than the computer value. And so we're going to actually have to now go and make this test work using the Agile method. We are going to drive the fix with this test, and then we'll expand the test to include the next feature. So let's go after that. Okay, so let's go and find our dual path adder and modify the front end of this adder to actually support denormals as 0 by looking at the types that come in and making sure that we are converting them to 0 when they are subnormal. So let's see. The first time that the inputs are used inside of this adder is when they're swapped. And so here we can see the only thing that's going to affect the whether they're normal or subnormal is right before this swapper. So here we're going to actually create some new copies of the inputs, and we're going to actually convert them to 0 if they as appropriate by the flag. So let's say we can create a final if A equals let's say if it's subnormal. And remember, this is the Boolean, so we're going to say this is a conditional check. Then we're going to we're trying to assign FA, so we're going to say we're going to clone A. Okay, and then we're going to fill it using getS with something that is dependent on whether it's subnormal or not. So in this case, if it's subnormal, we're going to say then return A, otherwise 0 it out. That's cleaner. Okay, there. So now we have FA. Let's copy this for FB. And we'll just change the A's to B's. and we will swap those values instead of the original A and B. So this is really the input of the adder. It's just once you have this swap done. Okay. There we go. So now we get all these converted. Okay, so now we've done the front end, and now we're going to basically, if we walk through this, we're going to say if A subnormal as 0 is set, then we're going to check if it's normal. If it's normal, we're going to just use A. If it's not normal, we're going to use 0 for the A input, and same for the B. And so now let's see if our test runs. And our test passes. So now we've actually done a smoke test of the DAZ, the normal as 0 input step, and we can consider either continuing and making a loop, or we can actually add the flush to 0. And I think what we should do is do the flush to 0 case next, and then we can actually use the same sort of smoke test, which is these subnormal inputs, and make sure that that they work in by adding the next two cases, the flush to 0 is true or false. So we'll work on that next. Okay, let's convert this DAZ test to a DAZ/FTZ singleton test. So we'll convert that. We'll add another loop, which is going to be flush to 0, which is the output side. And we're going to actually have to add a flag for the constructor for the output to actually turn on and off the subnormal is 0 case. All right. And then if we look at the output side, right, we're going to have to be very careful that while we do want to pull off the native computed value off of the floating point and not convert it ourselves, we want to take those native bits off. We do need to do the expectation comparisons. These will be subnormal 0 is FTZ, whatever we set for FTZ, same thing for the next one. So I'll grab that. And all right. And now we have a complete test. So now let's see. If we run this, we would expect it to fail because let's make the passing case first. If we don't change anything and we use flush to 0, things should pass. All right, that passes. And now we're going to add the flush to 0 case true. Run it again, and this will fail. All right, so now we have our failure. We expect this, and you can see why, this computed value is subnormal, and it should have been treated as 0, and it wasn't. And actually, we need to add another print just to make it clear what we're doing here. Run it again, you'll see the flag is set. So we have FTZ to be true, and it's not being flushed. And so now we need to go and actually update our dual path adder to do flushing at the end. So we'll go and find that. Okay, so let's go look at our floating point adder, and let's go to the bottom and see where we can modify it to do the flush. And remember that for the agile design paradigm, we're going to actually just get this functional first, and we're not going to actually try to optimize for hardware in the case that we're setting up either DAZ or FTZ. We're just trying to get the test to first work, and so that'll be the, and once that's working, then you go in and when you're optimizing, you can actually use the test over and over again to make sure that you didn't break something as you're optimizing. But first round, just get it working. And what we can see is that since it's a dual path adder, there's an R path and an N path. So it's rounding or remote and then near. And so we have these two paths that we need that converge at the end, and they both have their own computed mantissa that they're assigning. And so to simplify things, I'm just going to cut and paste the logic that you need for each of these. But basically, it would be checking, is the output supposed to be subnormal or not? I mean, is it supposed to be treated as 0 or not? And so we're going to do some of that logic here. So first, we need to we need an actual logic signal that tells us that the output is supposed to be treated as 0 when it's subnormal. So that's just taking the Boolean flag and converting it to a logic signal. And then for the R mantissa, we have this logic which is just going to mux either the 0 or this existing mantissa, depending on whether that flag that logic is true or not. So there. So we're saying if this flag is set, meaning if the output is supposed to be treated as 0 when it's subnormal, and it is subnormal, we're computing a subnormal path, right, on the R path where the exponent has no ones, then we're going to return to 0 for the mantissa. Otherwise, we're going to grab the previously computed mantissa. And similarly, for the end path, the near path, we're going to have a similar logic. So we're going to do basically the same logic condition with the same mux, but just with the final significant end path. So no difference really here, just computing it that way. All right, so let's see if that's enough to fix our adder to do the right thing. So we'll run our test again. And indeed, we pass our smoke tests in all the combinations of DAZ and FTZ for the different inputs and outputs. We actually pass this simple smoke test for a single pair of values. And so really the next step now is to actually do this exhaustively, which we'll do next. Okay, so to create an exhaustive form from our singleton, let's just grab the entire singleton and copy it. So we're going to basically just create the loops that we need for looping through the different exponents and mantissas. So we'll call this exhaustive. And then we will create these loops for the case of the first argument, the first floating point value here. And then we'll do the same thing for the second floating point value. So let's do that here. And then, of course, we're going to need to add in the 4 brackets, and we can get rid of these constants now. Okay, so now we have an exhaustive test, and we'll let this one run for, let's see, we're going to do 3 and 3, so 3 exponent wide, 3 mantissa wide, doing adds and subtracts, changing the first argument from DAZ from not DAZ to DAZ, same for the second, and finally for the flush. So all combinations of signaling of this subnormal as 0 test case. So let's see if that works. And here we're running all through all the combinations. And again, it's exhaustively going through all possible exponent and mantissa field values. And this should finish in 20 or 30 seconds, something like that. Given the narrowness of the widths, it's reasonable to run this somewhat real time. And if we were to find a bug, what we would do is we would take the values that we hit upon the bug and we would copy them into the singleton and then run the singleton and verify there. So now we've completed this test. We have an exhaustive test of our dual path adder, and it supports the new DAZ and FTZ features, but using type systems. So much more software-oriented and abstract way of dealing with a feature like that. And we showed this, the way of doing this is to use test-driven design by writing the test first, getting it to fail, even in some cases defining the API on the test side of what you want the component to do, and then driving that software change through the system, causing the test to fail, and then fixing the logic until the system passes. And the other thing that you saw was that we were using very much a software model first, making sure that we understood what the computation was on the software side before we made the surgical changes in the hardware to actually make it comply with that computational model. And so with that, I hope you enjoyed this idea of using an advanced data type and using agile methods to drive a feature change into one of our floating point components.